Lee Hamilton systems, and we're gonna do geometry with this Lee Hamilton systems, but I wanted to try to do something applied. So somehow I've gotten to relate them a little bit to the current pandemic or some kind of viral dynamics. So at the end of the talk, I will give some kind of conclusions concerning if it could be applied, if it's a good model to model the current pandemic, etc. So I'm gonna start introducing a little bit of the layout of the talk. So I want to start like telling you why we could be interested in Lie systems and what is a Lie system and how it could be related to the current pandemic, if so. And then we will start a little bit with the geometric fundamentals for these systems, and we will define what is a Lie system, and we will take a look at their solutions, which are interesting to me because they are nonlinear systems, but they admit a superposition rule, and this superposition rule happens to be nonlinear, and this is based on a good feature, on a good geometrical feature of these systems that we will see in forthcoming slides. And then some of these Lie systems are Hamiltonian, so that's putting even more geometry into them, because that means that we can take a look at them from the point of view of symplectic geometry and from the point of view of Poisson geometry. So we will review some remarkable geometric property of these Lie systems that happen to admit a Hamiltonian formulation. And we will retrieve through some methods how we can get solutions in terms of superposition rules using their geometric structure underneath. And the last question would be if we can write down a Hamiltonian formulation from the point of view of Lie systems for a pandemic model that could be similar to what's happening with COVID. So I'm going to start with the motivation. So why are we interested in Lie systems? Well, we are interested in Lie systems because they admit, as I just said, superposition rules. And these superposition rules are generally nonlinear. So this is like a different thing from what we are used to in linear systems. And this superposition, their general solution will be a superposition rule that's gonna depend on m particular solutions and certain constants to be determined according to the initial conditions over the manifold, as many constants, of course, as degrees of freedom that we may have. One feature about these Lie systems is at first, they are like first order ODEs. But we will see that this can be generalized to higher order as well. And also, there is an ongoing theory to also apply them to PDEs, but this is still being constructed. So basically, they are on a first approximation defined at first order ODEs, but we'll see we can do more with them. And what they do is that they enjoy lots of geometric properties, and this is the most important one for me in this talk, is that they have underneath a geometric structure that admits a finite dimensional Lie algebra or Poisson algebra. Also, the systems can be studied from the point of view of group theory, so they can be interpreted by Lie group actions as well. Also, the ones that admit Hamiltonian realization will be Poisson algebras, and we can apply something called co-algebras for obtaining solutions. And furthermore, I'm just going to talk here about Lie Hamilton systems, which are like the ones connected to Poisson. Well, we could also talk about many other compatible geometric structures, which are Dirac, is probably the most important ones, and also contact. And also for those interested in all the other things, is that superposition rules can be interpreted as zero curvature connections as well. So those are some nice geometric properties. So
also, Cristina,
Yeah.
One thing. So apparently there's a question by Dima, and maybe it's best if you just unmute yourself and ask, I guess.
Yeah, of course.
Yeah. Yes. Sorry about the interruption. So those phi's, they take arguments from n to the power m times n into n, right? Is that?
Yeah.
Could you backtrack one slide? Yes. Yes. So, but why are those arguments there? The x, comma, the x of t's, all those guys. Why are they in n?
N is the manifold, but then I'm gonna consider R something. Depends on what dimension I am. It probably will be.
I thought that n was the set of natural numbers right there, because it says that
no. N is the manifold. Well, I have my system, and empty.
Okay, so the other n is kind of like so this like the normal n is a manifold, and the other n there is
this m is
number, right? So the set of natural numbers.
This m is a natural number that I will tell you about it in the next slides, because it's the number of copies it's the number of particular solution that one has to use.
Right, but I mean, like the argument k there, the last argument, that's a number, right?
Those are constant. It can be a set of constant, like this x can be x1 to xn. Okay, you can have n degrees of freedom. So this k, in order for the system to be integrable, it can be nk. So they are constants of integration that you will find according to the numbers of degree of freedom. So if this x is a vector, you will need 3 constants of integration. So it depends on what dimension you are over the manifold. But we will be in R2 mostly for the examples that I'm going to show you. Okay.
But Dima, I think there is only one n. There is no natural numbers there.
Okay, but so the last argument, like this k, but it says that k is an n. Right, so there's like m first arguments and then another one, so m plus 1. So is it just the manifold n to the power m plus 1, or is it the manifold n to the power m times the set of the natural numbers?
This one
is what's the domain of phi?
Look, this one is times m, because you will have to copy it m times because the particular solution.
Yes, and last
then this one is for k, and this one is the result. We don't know how many degrees of freedom we have. Imagine that the system is
the manifold n.
K
right?
is also a point in the manifold n. Am I correct?
Yeah.
Oh, okay. All right. That's fine. That's
And you get a solution for.
Okay.
Yeah, and you get a solution for the manifold.
Yeah.
Okay.
Yes, yeah, I'm good. Thank you.
Okay. Yeah, don't worry. All right. So about the some of the applications can be some relevant physical models. These systems appear in mathematics. They appear in control theory, especially in control theory in Riccati equations, as we will see. Like matrix Riccati equations that are very common in control. They appear in quantum mechanics, as it can be the nonlinear Schrödinger equation. And also in biology and ecology, we will see an example of viral dynamics. So the question is, are there any epidemic models or are Lie systems? Well, I'll show you one in these slides, in the next slides. Apart from that, Lie systems and superposition rules, as I told you, have been extrapolated to higher order systems of ODEs. And also, as I told you, even some PDEs are being studied from the point of view of Lie systems. And well, some other examples are the second and third order Kummer-Schwarz equations. I don't know if you are familiar with them, but they are some equations that appear in quantum of non-equilibrium dynamics of many body systems. And they are connected to the Schwarzian derivative. both of them are also connected to time-dependent oscillators. For example, the Milne-Payne equation is a type of nonlinear oscillator that is almost like the harmonic oscillator, but it has a third-order cubic term in the denominator. So they're basically very connected to these things, Lie systems in general. So they have lots of applications in all kinds of literature. Okay, so I'm gonna tell you a bit of geometric fundamentals about this Lie system. So this is the notation I'm gonna use. I'm gonna use a Lie algebra, and it's gonna be a pair, as we know, of a vector space, and it's gonna be equipped with a bracket that is bilinear. And we are gonna define this set. This set that I will call sometimes by Bx is called Lie B, V, and the bracket. It's the smallest Lie subalgebra of V that is gonna contain a subset V. That is the space generated by all the derived series of the subset V. So we have to define also what is a time-dependent vector field. And a time-dependent vector field is gonna be defined like a vector field that we are used to in the tangent in the same way, as long as we interpret a time-dependent vector field as a parameterized vector field by a parameter t. So basically, if this diagram is commutative, so here in this case, we have an extra for the time. And if this diagram is commutative, it means that the vector field is like an usual vector field, which is just the anti-image of the usual canonical projection. So these maps can be understood as regular vector fields. So that's a concept that we are gonna need to introduce what is a Lie system. And also an integral field for a time-dependent an integral curve, sorry, for a time-dependent vector field is going to be the integral curve of the suspension. The suspension is just the vector field plus partial derivative with respect to t. That's the suspension. It's usually called this way. So now a curve, an integral curve for these time-dependent vector field is going to be a curve that's going to take values here, and it's going to have, like any vector field, an associated system. As you can see here with the projection, you will have an element in n, and since you are deriving with respect to t, you will be in the tangent. And here, by composition, this will be the same case. So that means that we are able to define through a time-dependent vector field an associated system the same way as we do for a regular vector field. And it's going to determine a single first-order OD, and conversely, it happens the same, that given such system, there is a unique time-dependent vector field whose integral curves are the particular solutions, okay? So what I introduced in the previous slide, this Lie of BV bracket as the minimum Lie algebra that contains all the series expanded by V. Here, we will call the minimal Lie algebra of a time-dependent vector field as the Lie, the same subset that I have defined here, which is basically all the commutators at different t's. All the derived series again, t, x at t2 with x at another t3, etc. And this is what we will call minimal Lie algebra. And this minimal Lie algebra is called Bézier-Goulbert Lie algebra. That obtains all the expanded series at any time. Okay, so here I introduce you the theorem for Lie systems. So we say that a system, a first order system in the first approximation, then this can be generalized to higher order systems. A system like this, as we have said, it has an associated first order system and a vector field, time-dependent vector field that we show that there is a bijection, and it can be written this way, right? So we say that a system is a Lie system and admits a superposition rule if and only if this xt can be written as a linear combination of certain vector fields that are time independent, and the time dependency can be put in the coefficients. Okay, so if these vector fields close a final dimensional Lie algebra, we will say that the system is a Lie system. Or likewise, that it admits a superposition rule. And this Lie algebra, this finite dimensional Lie algebra formed by these vector fields, is called the Sealed-Goldberg Lie algebra, which is the minimal Lie algebra that we were introducing, and that will be given us the derived series at any time, etc. Another way of enunciating this theorem is the saying that a time-dependent vector field, we put the T here, admits a superposition rule if and only if the Sealed-Goldberg Lie algebra associated with it, it's finite dimensional. So to clarify this, I'm going to show you an example. So this is the Riccati equation on the real line. It's an ordinary differential equation, and as you can see, there are some time-dependent coefficients here. And as we said, we can write it in terms of a time-dependent vector field. In this case, it would be this one plus a2 squared, with respect to x. And what we have to find is that this time-dependent vector field can be split as the sum of certain coefficients that depend on t and certain vector fields that do not depend on t. And as you can see, this xt can be written as a0 x1, where x1 is this one, plus a1 x2 plus a2 x3. So the first condition is satisfied, and the second would be that these vector fields cause a finite dimensional Lie algebra, and they do. The Sealed-Goldberg Lie algebra is isomorphic to the special linear Lie algebra over the plane and the reals. So this means that the Riccati equation on the real line is a Lie system, and for it, it admits a superposition rule. And here is the superposition rule that it admits. As you can see, in this case, it depends on three particular solutions. So this is what I introduced before, like the map that I was saying, like from n times m, n to n. As you can see, m is the number of particular solutions. So in this case, it would be 3. And the number of constants of integration is only 1 because we only have 1 degree of freedom, which is the x that we have to resolve. That's this n for, and it gives us a solution on n, which is x. So we can see that the solution is a general solution, and it's written in terms of 3 particular solutions. So one may wonder, how many particular solutions does one need to obtain a superposition principle? Well, there are different ways of enunciating it, but you can think of the Frobenius theorem. And as you can see, we have 1 degree of freedom for x, which is only the x that we have to look for. And we have a 3-dimensional Lie algebra, which is the SL2R. So in the venicity of the Frobenius theorem, it tells us that we can get so many first integrals, the number of first integrals that you can obtain is would be the number of degrees of freedom minus the dimension of the algebra. But in this case, if you have 1 degree of freedom in a 3-dimensional algebra, it's impossible that you get a fresh integral. For that matter, you have to somehow get particular solutions that we will call copies. So if I copy the system 3 times, which this will be my base system plus 3 copies, let's call x1, x2, and x3, which is called diagonal prolongations, I will have 4 degrees of freedom. And if I rest 3 minus 4 minus 3, which is the dimension of the Lie algebra, I'll have 1, and I'll have 1 first integral. This is exactly for this very specific and simple example. I just need 1 because I have 1x only to integrate. So this is something that we will see in forthcoming slides, like how to get one of these superposition principles. Also, for those who like working better on the group, one can see that every Lie system has an associated Bézier-Goulbert Lie algebra. And you can integrate this Bézier-Goulbert Lie algebra, and you're gonna get Lie group action. And this Lie group action has fundamental vector fields, whose elements are just the tangent space of the group evaluated.
Chris, sorry, I think like Dima wants to ask again, maybe?
Yeah.
Please, yeah, I'm sorry for interrupting. Could you please go back to one slide, backtrack on one slide, the previous example?
Yeah. Here I am.
So what is the phi in this case? Is it this well, the formula in the middle, the fraction?
Yeah, this is the solution.
So
and it's
so the thing on the right hand side, is that the phi?
Sorry, I couldn't hear you. Like I think your voice cut.
It's phi the expression on the right hand side of this formula.
On the right side?
Yes, x of t equals, and then there is this expression. Is that phi? Is that your phi?
Yeah, this is my phi. Like
okay.
My phi.
Right. So that's the phi right there. Okay. So my question is, well, so it has a denominator. So it doesn't seem to be defined, you know, everywhere on R3 cross R.
Yeah, exactly. Like when you really write the solution, you have to make sure that you say, yeah.
Okay, so in general, it's not defined on this n, well, this product of several copies of n, but only in some open subset.
Yeah, yeah, exactly. In some open subset.
Locally defined function.
Yeah, the thing is that I haven't put exactly where, because this these are particular solutions, so it depends on what particular solutions you choose in each case. Of course, the open subset where the solution is defined is going to be different, but of course you have to take into account that, yeah. Right. But a formal solution would be this, so just put in all those, yeah, for each specific case you have to realize the domain in which it is defined. Actually, this is an example that I'm not really showing all, but I'll show you in the next ones where we have to restrict in order to make sense. Yeah. But this would be my phi, exactly, where m equals 3 in this case, because it's 3 particular solution, and n is where there's one constant.
Right, so you substitute those solutions only after the fact, because, well, the formula for phi seems to be universal, right? So it's just...
Yeah, it's universal, so you can choose particular solutions, and you can choose them depending on your need. Actually, for COVID, you will see that I have
and so you didn't actually tell us what solutions those are in this particular case, right? I presume that they depend on the A's here.
Yeah, these ones, I don't have them written down. Those ones are actually not so easy to find, and some people have actually computed them with numerical methods. So these particular solutions are quite difficult sometimes to find. These ones I have not written down here, but for the case of viral dynamics, I will show you the superposition with some particular examples.
All right.
So also, yeah, one can say, well, I want to study Lie systems, but I like the group. theory better instead of Lie algebra. So every Lie system is associated with as we have seen, with a finite dimensional Lie algebra, which is called the Bézier-Goldberg Lie algebra. And you can integrate it to a Lie group action. And the fundamental vector fields of the action are just going to be the tangent to the group evaluated in the identity. So in this case, the general solution to the Lie system will be given by the action, one particular solution on the group, and certain initial condition over the manifold. And this particular solution is the solution of this equation, which is, as you can see, another combination of time-dependent coefficients and some fields defined on the group that close a finite dimensional Lie algebra. And these fields are the right invariant vector fields as a certain basis in the group. And so as long as these right invariant vector fields close a finite dimensional Lie algebra, you can solve the equation for a particular G and insert it in the action, and you will also get a general solution. So it depends on what you prefer from the Lie algebra point of view or from the Lie group point of view to use these systems. So I'm gonna tell you a bit about a contemporary application, which would be Lie systems in viral infection dynamics. So first of all, I'll start with a simple viral infection. So you have two variables. Imagine that these are the infected individuals, for example, and X are the susceptible ones. So as you can see, if a susceptible individual meets an infected one, of course, there is a probability that it's going to get infected and it's going to make the number of infections bigger. So you have to add a term like that to modelize it. And also, it can be that the number of infections go lower because some people are obviously going to recuperate. Well, the number of susceptible individuals, which are the X, of course, it grows. The more population there is and more people come into the place, the number of susceptible individuals is going to grow. And also, some people are going to get infected, so they won't be susceptible anymore. They will pass to the equation of the ones infected. So that's where it's minus. And it depends, of course, in the number of infected ones and how they're going to interact. So if we take the non-trivial solution, which would be that X and Y are different.
Sorry, can I ask a quick question?
Yeah.
So I'm having a bit of trouble with my connection, so sometimes I miss things. Could you repeat what the alpha of T term represents?
The alpha? Yeah, I'll repeat everything. So you can take this simple viral infection. For example, this can be the infected individuals, and this can be the susceptible. So you have to have in mind that there are some processes are going to make the infected grow or decrease numbers, and the same with susceptible ones. So imagine these are the infected ones. How are they going to grow? Well, in the moment that infected are going to meet up with some susceptible ones, they're going to infect him. So when there is an interaction, this is going to be positive and they are going to grow. But this gamma, it's a factor that is the recuperation parameter. So when they get recuperated from the infection, they are good again. So that's why it's a minus, because it's going to rest in the number of infected individuals. And about susceptible ones are this X. And of course, the more individuals there are, the more that they are going to grow. You know, the more that they come into a simple infected area. But you have to rest that some of them might not be susceptible anymore because they're going to get infected. So that's why it depends on the number of infections.
So I was wondering what the time dependence of alpha and beta would be.
Oh, I don't know. There are lots of models. You can change it actually, but for this model for list systems, I'm not gonna use any one in particular. But there are like many different ones. Actually, I saw like a final master's thesis of a girl the other day, and she was using like lots of different parameters and telling you the different curves of infections. So in this particular case, I don't know, but I'm just telling you the interpretations of the signs and how they grow. Yeah, so, well, so this would be our system. So as you can see, as I said, you can write a time-dependent vector field associated with it, right? It would be something like this, minus gy x, and this is partial derivative with respect to x, plus dt xy minus gamma t I y. And this one can be split, as I told you, again, into finite dimensional combination of vector fields, okay? And the vector fields in this case are these three. And they close a finite dimensional algebra, which is just the product of the line and the plane, okay? But it's a Lie system, so that means that this viral infection admits a solution in terms of a superposition rule again, okay? So I wanted to start with a simple viral infection to tell you a little bit about this other model, which is called the susceptible infection susceptible individuals. So that means that this particular model does not really include immunity. It means that you are either susceptible, you can get infected, and after being infected and getting cured, you can be susceptible again. Okay, so it means no immunization. This model, I took it from, I'll give you the reference in the next slide. So this is a model that it takes you tells you the instantaneous density of infection individuals, and we are going to suppose that it's taking values in between 0 and 1, and the fluctuations have been neglected for the moment. So the density of infected individuals is going to decrease with this rate because some will be recuperating. And the new infections will be proportional to this number, which is this are the infected. And of course, since the instantaneous density goes from 0 to 1, then 1 minus rho will be the number of susceptible ones. Susceptible ones. So as you can see, this is a very similar thing to what I was showing you before. This XY factor, when they were with the BT, when they were meeting each other, and this other one, because they are recuperating. So, well, in this model, we can just make a time for escalation, and we get to this differential equation. Obviously, the equilibrium is gotten if rho equals 0 or rho equals rho 0, which is given by this parameter that depends on the recovery rate, and this is a rate for the growth of new infections, okay? So this model involves something that is called the random mixing hypothesis. That means that all kinds of population mixes with all kinds of population, which is not really true because not everyone in the same neighborhood mixes with people from another neighborhood. And also it's very large population assumptions. So it does not really work for everything. And also we are not admitting any fluctuations. So if you want to put some fluctuations into this model, what you have to do is to introduce stochastic mechanics. Since temporal fluctuations are good because they just basically alter the prevalence of the pathogen and the spatial heterogeneity. So basically it relaxes a bit these assumptions that we are supposing is actually making this model a bit more real. So from this paper, I was telling you about Hamiltonian dynamics of the cis epidemic model with stochastic fluctuation by Nakamura and Martinez. What they do is not really an stochastic expansion. What they do is just to suppose the spreading of the disease as a Markov chain in discrete time. And in this time, at least one single thing happens. It's either one transmission that someone gets infected or one single recovery that you get back to susceptible. So this is the equation that tells you how you can pass from an instantaneous probability of finding the system and the mu state from finding the system in the p nu state. And the figuration is given by this Markov chain. Basically, depending on which n equals 1, it means that the K agent is infected. And if it's 0, it's not. So basically, these n's will give us the configuration of the systems and individuals. And basically, the transition rate from one probability or the other is going to be this Hamiltonian. It depends on the two sub-indices that basically just link you from one state to the other state. So from these considerations, the evolution on times, the statistical moments, that is the instantaneous number of infected individuals goes like this. It depends on the bracket of each state. From here to here, you're gonna make a jump, and these are the equations that I took from them. And these are the equations that they give for the dynamics of the infected individuals. In here, sigma square is the variance, is the error that you can make from making this distribution of probability. So if you take that system of equations, which is this one, it can be seen that it can be Hamiltonized. I put this because there's other kind of Hamiltonization in mechanics. So, but this Hamiltonized, I want to say, to find Hamiltonian. So if in this system, which is the system that they introduced by introducing this Markov chain, that makes up for the fluctuations, if you call the density of infected individuals Q, and you call P the inverse of the variance, well, the square of the variance, because the variance is sigma squared. If you write it in Q and P, you can find a dynamical system in two variables. It's on the plane, but it looks like this. And this can be proven that it comes from Hamiltonian. And this is the Hamiltonian, okay? So one can get a Hamiltonian system just starting from a simple cis model that everyone knows. Just by getting some kind of fluctuations on a Markov chain, we can write a Hamiltonian system. So that's pretty interesting. So that means that if this Hamiltonian system is a Lie system, we could find solutions in terms of a superposition rule. I'm just going to show you this. If you solve this system, solve analytically with, I think I did it with Mathematica. I just found those two solutions. Okay, I'm just letting you know that it depends, of course, on two constants of integrations. And if I find Q and P, I can just invert and square and get the variance and get the number of infected individuals, okay, from these results. So I wanted to find three particular solutions because I may need them for the Lie systems theory. So before starting with the Lie systems, I tried to find three particular solutions. So this is a particular solution of the system, of that Hamiltonian system. And as you can see, it starts growing, and there's like big acceleration in the growing, and then it gets to what everyone calls the flattening of the curve that we have to achieve. And this is just a representation of the error that we are committing. And it makes sense because in this part, since we are having very accelerated growth, we can have big errors in the ones that when we are just reaching the plateau or the flattening curve, of course, we have less error. In this case, you have to choose wisely the constants of integration. It's very small, you cannot see it, but well, C1 equals 10, C2 equals 1 in this case. So that would be one particular solution. Another particular solution is by different choices of the constants of integration and different choices of the row. So this other one is given, well, this one is the 3, is the second. Which one am I showing? Yeah, this one is more interesting. So this one, you have the C1 equals 3 and C2 equals 1. So basically, I set boundaries where this model works, because the growth, it should be something like this. This is actually a sigmoid function. I don't know if you're familiar with the sigmoid function. That is a very common function that appears in this kind of event in lots of natural processes, and learning curves of also complex systems, they appear. And also it's called a logistic function. It's a particular case of this one, or the curve of Gompertz. I don't know if you have heard about it. So the curve of Gompertz, it's used for models as well that they start growing, like magnetization of some magnetic things in physics, and they get to a plateau. So these are like kind of sigmoids stuff functions that one could expect. And well, actually this behavior is only given that if one of the constants of integration is 3 times bigger than the other, at least. Otherwise, you find kind of weird solutions, and they wouldn't be particular solutions. But this ones do fulfill the equations. So these particular solutions, as I told you, I'm just showing you because I might use them for the Lie systems approach. So now I want to show you that that dynamic system in which I found a Hamiltonian is actually a Lie system. So I now call it SysF, or F for fluctuations. And I can write that system as this, like a linear combination of a time-dependent coefficient and 2 vector fields. There are these 2 that are time-independent, and they close a finite-dimensional Lie algebra. Here it is. This Lie algebra is called infinite Lie algebra 114. There's a whole classification for finite Lie algebras on the plane, and they are classified according to primitives and semi-primitives, and this happens to be the 14th primitive on the classification table. So, so we have gotten to know that this SysF with fluctuations is actually a Lie system. Well, it means that it meets a superposition rule, which is interesting, and we can retrieve some solutions for this system. So now I want to show you how to get a superposition rule. So as I told you, one has to bear in mind the number of particular solutions that one's going to need to make a superposition rule. So given the time-dependent vector field, it's related to the ODEs, we call the diagonal prolongation of this vector field to basically copy this vector field into different variables. So you get the vector field, and it's like summing the vector field in, if we have variables Q1 and P1, it's just like summing the same one in Q2, P2, plus several copies, as many as you need. That's the diagonal prolongation. And of course, it fulfills that when you project the diagonal prolongation. Here I have a 1 because this, I put the 1 for the base system that I have, okay? And it starts from 1 to m to the number of copies. So if I project it, of course, you obtain the initial dynamics. And it's also interesting that this copied system is invariant under permutation of the subindices. We will see this with an example. And this is a good property to obtain first integrals for the system as well. So if we write now the system associated, it's of course the coefficients of each of the variables that we have. In our case, we have x and p, so this would be an x, or it would be a p, both. And then you have to sum all over the number of copies that you're gonna make of the system, which is basically this. So Then, to get the first integrals, what you take is the basis of the Basile-Kuhlberg algebra, and to know the number of copies that you have to make is to choose the minimum integer, which is that m that we saw in the phi, so that the diagonal prolongations of these all vector fields are linearly independent at some generic point. Basically, it's what I said, it's the Frobenius theorem. So we have to count dimensions. You have to count that the number of degrees of freedom has to exceed the dimension of the Lie algebra in such a number, at least that you have as many first integrals as you need. So you obtain n functionally independent first integrals. Imagine that the base manifold has dimension n. So in order to make it completely integrable, you have to find n functionally independent first integrals, and they have to be, of course, common to all the vector fields. And well, they have to be linearly independent, and it can be solved. These first integrals can be solved for the method of characteristics in the vector fields. And then each of these first integrals are going to be constant over the manifold. So basically, what you're forming is a foliation of the space by choosing different constants for these first integrals. And then from here, you can obtain the initial variables, and you will get what is called superposition rule. So I'll show you with an example. So if we do it with the SIS model that I was showing you with the fluctuations, as we said, step one is to see that it's a Lie system, and it is, as we said. We have a closed finite dimensional Lie algebra, and it's E14 in primitive number 14. So we have to go a step further, and you get to step 2. So now my base manifold has dimension 2. It's on the plane. It's 1x and 1p. If you remember, the x comes from rho, and the p came from the inverse of sigma. Okay, I have 2 dimensions, but I have a 2-dimensional Lie algebra. And how many first integrals do I need to solve this? I need 2, one for x and one for p. So the number of first integrals that I need has to be number of degrees of freedom copied minus the dimension of the Lie algebra, which is 2, and we have 2 here. So at least I have to copy the system once, so I have 4 degrees of freedom, and 4 minus 2 gives me 2. I could copy more times, but it's just going to make it more difficult to integrate such vector field copies so many times, but I could get more first integrals and choose what I want to use. But since I only need 2, if I have 4 degrees of freedom, I'm done. So I start with my system, which is Q1, P1, and I said, okay, I'm just going to copy it again to obtain the 4 degrees of freedom. Basically, that means that each of the vector fields of the Basile-Kuhlberg algebra have to be prolongated. So if you take x1, which would be this one first, as you can see, I have copied it. Basically, it's like put in extra variables. Now it's Q2 and P2 instead of Q1 and P1. Okay, and I have to integrate this and find a first integral. And of course, this first integral has to be a first integral of x2 as well, because it has to be a first integral for xp, and xp is the linear combination of both. So if I want it to be a first integral of the prolongation, it has to be a first integral of x1, and it has to be a first integral of x2. So that's what I'm going to compute. So I prolongate the vector field, as I said, and I take the following characteristic system, which is the associated characteristic system, and I just make one of the variable fix. I'm going to fix this one and integrate all of them with this one. So I get 3 new variables, which are Q1, Q2, and Q3. K1, K2, and K3. And since they have to be first integrals as well for the x2, what I have to do is convert x2 in this new variables that I have reduced. So this is the passing of the new variables in the tangent space, and I write x2 in the variables and integrate again. So now I think I fix this and I integrate this with this and this with this, and what happens that you get to the following thing. You just get to two first integrals that are going to depend on two constants of motions from the integration. Realize that these are capitalized, that are from the previous one, and this K1 in lowercase just came from the next integration. So from here, you can get the superposition principle again for the base manifold. Because you remember that you had this and you had added this to just get to the solution. These are like fictional. Actually, they are going to appear in the superposition rule. So if this is set equal to a constant over the manifold and equal to a constant over the manifold, and we undo all the changes because this was depending on x and p, if you remember when I integrated, sorry, q and p. And we make the changes all back, undoing all the changes of integration, you just get this solution, which is obviously a nonlinear superposition rule that depends on two constants of integration. Makes sense because we have 2 degrees of freedom, and it depends only on one particular solution, which is Q2 and P2. So in order to obtain a solution, one has to plug in here a particular solution, and you will get a general solution for this system of susceptible, infected susceptible individual, but including fluctuations in this case. So here's what I did. I show you, if you remember, solution 1, solution 2, and solution 3, and I told you that they were only solutions if C1 was at least 3 times greater than C2. So I get one of them. I think I took this to the solution number 2 that I showed in previous slides. And I just plugged it in what I told you. I just plugged it in here, in that one, and put it here, and go back. And this is the solution that I get. Again, it's kind of sigmoid type as well, as you can see. So all the solution makes sense. It seems that this is the curves that we have been obtaining from the COVID thing. Something like really accelerated growth until you reach the flattening of the curve. Here I have represented rho with time, and rho is q, so I'm just basically representing the q that I have solved. I could represent the error, but I have not given the error here because K1, one of the constants of integration, tends to 0. So the error is really almost 0 everywhere. So it was not an interesting graphic. So basically up to here, you can see that we have been able to obtain a general solution depending on one particular solution, in this particular case of a C's with fluctuation model. It's 5. Do I have 10 minutes more because we started a bit late?
Yeah, I think that's okay.
Okay, I will comment something on the Hamilton systems because you can have further properties in the case that you have that the Lie system is Hamiltonian. So I'm gonna go faster. So I have time. So, well, use a geometric reminder. Now we are going to deal with Poisson algebras, okay? And we are going to have Hamiltonian vector fields, and they are obtained through the Poisson bracket as usual. We are going to have the Jacobi identity for the Poisson structure, and it entails the change, the Lie algebra and the homomorphism as we were having between this finite dimensional vector fields of the Basile-Wilber Lie algebra. And now what we are going to have, instead of finite dimensional Lie algebras of vector fields, we will have finite dimensional Lie algebras of functions, because it's a Poisson algebra. So we're going to see how we can translate this. Yes, remember that as every Poisson structure is a derivation is each entry, you can define a bivector, a Poisson bivector that's defined through the Poisson bracket, and we are going to make use of all this machinery to talk about the Hamilton system. So how do I know if a Lie system is a Lie Hamilton system? So we consider again the Riccati equation. If you remember, this is the first one that I introduced. But in this case, the variable is not x, it's z, it's on the complex plane. So this can be split in x and y, okay, in two equations. So if we write the system as a time-dependent vector field, it can be written this way. Again, it's a finite linear combination of coefficients depending on time and vector fields. And this vector field, as we then close a finite dimensional algebra. Of course, it's the same one that it was closed by the Riccati equation on the real line. Okay, it's this special linear group as well. So we wonder if it admits a symplectic form. So we're just gonna try to look for it. So we suppose there exists a symplectic form, and we wanna know what's the coefficient. So we have two terms somehow, the Basile-Wilber Lie algebra associated with the Lie system into a Lie algebra Hamiltonian vector fields with respect to it. So we have to impose that the Lie derivative of the symplectic form that we have to look for with respect to each of the vector fields of the Basile-Wilber Lie algebra is 0. So if I just take a general function here, I will get this for these particular vector fields of the Riccati equation, and I'm able to compute an f with the first condition. And with the second condition, I get the coefficient. So it means that for the Riccati equation on the complex plane, I have an associated closed and non-generated form. So I have a symplectic form. And through this relation, I can obtain the Hamiltonian, from the Hamiltonian vector field, I can obtain the Hamiltonian function that is corresponding. So I calculate them with this omega and the vector fields of the Basile-Wilber Lie algebra, and I get Hamiltonian functions. So as you can see, it admits a symplectic structure and it has Hamiltonian functions. So it's a Hamiltonian system. You can go a step further and you can, well, we can define then a Lie Hamiltonian structure as a triple-like manifold. The bivector, well, here we were working with omega. In the cases that you can define the bivector, you have the bivector and the function h, which in this case is going to be a finite dimensional of certain coefficients and some functions that are going to close a finite dimensional Poisson algebra in this case. So in this case, a Lie Hamilton system defines a curve in a finite dimensional Lie algebra of Poisson functions instead of vector fields. In the same way as we did with time-dependent vector fields, now we're going to have to define time-dependent functions, which is going to be the Hamiltonian, and we're going to define the minimal Lie algebra, which is also going to be the Lie instead of the bracket of xt. It's going to be the bracket of the Hamiltonian function at ht. And that will be called the Basile-Wilber Poisson algebra, etc. The derived series. So we will say that a time-dependent vector field, as we had, admits a Lie Hamiltonian structure. It will be the Poisson bivector and this time-dependent Hamiltonian if there is a corresponding ht. Basically, as we will see, is that the anchor with the Poisson bivector of the differential of the time-dependent Hamiltonian retrieves the time-dependent vector field that we were using for our Lie system. It's just basically the same, but from the Poisson point of view. So in the case of the planar Riccati equations that I was showing you, we saw that we have Hamiltonian functions. And furthermore, these Hamiltonian functions close a finite dimensional Lie algebra as well with respect to a Poisson bracket. So this is the Lie, the minimal. So this is what we call Lie Hamilton algebra for a Lie system, okay? So when systems admit this Lie Hamilton algebra is really interesting because you can have a lot of geometric properties and you can obtain superposition rules using lots of machinery for them. But I'm afraid I won't have time to show you all that. But let's see just the viral infection model again here. As you saw, these were the time independent vector fields that close the final dimensional Lie algebra. And we can find an omega, which is this one, such that these vector fields are Hamiltonian, and these are the Hamiltonian functions. And these Hamiltonian functions happen to close a finite dimensional Lie algebra as well. And you can find that is also a representation of the system by a time-dependent function with a linear combination of time-dependent vector coefficients and time-independent functions in a Poisson algebra. In this case, look at this. The Lie algebra of Poisson, the Poisson algebra is not the same as the Lie algebra. Here you can see that we have 4 elements. This is called non-trivial central extension of the Lie algebra. So sometimes, in most cases, when you have an XT and HT, the Poisson algebra coincides with the Lie algebra most of the times. But sometimes there are cases for some particular algebras that the passing to the Poisson is not trivial, and there will be a non-trivial central extension, okay? This is one of the cases, but there is a whole classification theorem telling you when these Lie algebras will go for a trivial or non-trivial central extension. In this case is that. Again, we don't mind. It can be there, like non-trivial central extension. It's still a close finite dimensional Poisson algebra, and it has a Lie Hamiltonian structure. So I wanted to show you how to derive solutions again using the coalgebra method, but I don't have time, so I will just show you that this system with fluctuation is actually a Lie Hamiltonian system. So these were the fields, and you have, with respect to the canonical symplectic form, you can find these 2 functions, and these 2 functions can be written here. And you will have the time-dependent Hamiltonian that will, with this, split as a time, again, as a finite dimensional Poisson algebra with time-dependent coefficients. This Hamiltonian that I have retrieved using all my Lie system theory is the Hamiltonian that was proposed in this paper from which I was looking at the stochastic fluctuations. So this means that the Lie system theory is actually a quite legit geometrical point of view to see the system, because I have actually, by this machinery, obtained the same Hamiltonian that they have proposed, just by using geometric structures in this case. And apart from that, it's late, so I won't mention it, but you can derive a superposition rule, which is the important thing, using what is called the coalgebra method. But this is a long method, but you can take a look at the slides if you are interested. And it's a method that you have to use the coalgebras. So basically, it means the same thing as we were doing. We were copying the system. We were taking the diagonal prolongation, which was basically summing copies of the original XT. So here, this coalgebra method is letting us split the Poisson by vector and copies as well. Okay, so it's a way of interpreting that. And also the Hamiltonian function can also be prolongated in such way with something called the coproduct operator, which actually what does is just copying the system. if you are familiar with it, you will see it's the primitive co-product. So we'll show you. There's a theorem that tells you that using this primitive co-product, you can obtain the first integrals this way. So you take the Casimir of the Poisson algebra that I was showing you of these ages. It's 2, it's 3, and you take the Casimir. And what you do with the Casimir is copying, case the number of copies, number m, with the co-product as many times as copies as you need to integrate the system. And d means the representation. That basically means to take the values of h1 to h, whatever dimension of the algebra is. So when you do that, you can get as many first integrals as you need. So going a bit faster, you're able to retrieve a superposition rule as well for the cis-pandemic system. But in this case, this is the solution that I get. Wait, I have it written in other coordinates. Let me show you next slide. This one. So this is the solution again for my x and my p. Remember, this was the density of infection. It was divided by sigma. But in this case, my superposition rule depends on two particular solutions, Q2, P2, and Q3, P3. So in this case, we have three particular solutions and three constants of integration. This one is a function of these, so it's actually two. So everything makes sense because we only need two, one for Q and one for P. So it's another way, and I would like to explain it, but we're a bit short on time. I'm actually already late. So, but the equalgebra method is really good machinery from Poisson algebras, where you can do lots of things. So let me show you that this solution is legit too. Wait. So now I have plugged here two solutions that the ones that I showed you at first. I told you, oh, I'm just retrieving them because I will use them later. I have plugged two, and again, this is very blurry and you don't see it, but certain constants that I had to choose, it's a very big thing. But again, all these functions are usually behaving in the same way, like plotting in the curve again. Actually, all these functions are not sigmoids themselves, but they are of the family. Like they are like mixing of arcotangents that are very related to the sigmoid. Others are hyperbolic tangents that you get from mixing things that appear here, or the error function. So again, the solution is the expected one. So basically what it tells you is that using one approach or other that depends on different types of particular solutions, you can get a legit approximation of how it's been the growth of the cases. So here to finish, I just want to make some conclusions about this model could be any related to the COVID situation. So the cis with fluctuations model is a very first approximation for a trivial infection process in which you obviously have two possible states only. You are infected or you're susceptible. So this model does not have the possibility of acquiring immunity. So this is something that we have to consider because it seems that 30% of the infected individuals by COVID get some type of immunity. So actually should be a model that is including immunity and non-immunity in some certain individuals. So one could say like use the SIR model, which means R, it means recuperate individuals, basically that they are immune now. But it's neither a proper model for the current situation because some are not immunized individuals. Apart from that, if you try to use the Lee system theory in the SIR model, it's not Lee system, this one, so it's ruled out. But there are many models like SAIR and like with 5 letters. That means lots of things. I haven't tried all of them, but I have the suspicion that they wouldn't work neither. And I think that the only reason why the SIS model has function is because we added the fluctuations. So what we should do is maybe start an stochastic theory of Lie systems to find more models that are Lie systems, because the models without fluctuations, they don't seem to have this rich geometry background that I'm using to retrieve all these solutions. So, well, so my open question is that maybe stochastic Lie systems, it could take me to finding more Hamiltonian Lie systems that include immunity, non-immunity, you know, because the usual ones, as I told you, they don't work. So one should try to look for this thing in the next models, but unfortunately, I don't think this exists yet. Or if it exists, I don't know if it's Hamiltonian, because this was just a very lucky trick. And I'm well past the time, so I'm very sorry I took so long, but thank you for the attention. And if you want to take a look at some bibliography, we had a whole book that's about Lie systems and compatible geometric structures. And I have a lot of, most of the content is here. And the preprint from this SIS model with fluctuations is here. It was just sent for publication a couple of weeks ago, and we still don't really have any news. So, thank you.
Thank you, Cristina. Yes,